on the right-hand side diagram, I have plotted again the experimentally measured partial vapor pressure of the component B in a solution with A as a function of the mole fraction of B in solution. We observe that the vapor pressure of B is a nonlinear function of XBL, and that the deviation between the experimental partial pressure and the partial pressure expected for the component of an ideal solution on the basis of Raoult's law changes with composition and vanishes only when the mole fraction of B approaches 1, that is, when B is almost pure. We also notice that when B is very dilute in solution, that is, when XBL is close to 0, there is a linear relationship between the partial vapor pressure of B and the mole fraction of B in solution. This linear behavior is, however, not Raoult's law, since extrapolation of PB to XBL equals 1 does not yield PB star, the vapor pressure of pure B, but a different value which we have denoted as K prime sub H on this diagram. The observed linear relationship between the partial vapor pressure and the mole fraction in solution for any component of a mixture in the very dilute concentration range is called Henry's law. The constant K prime sub H is called Henry's constant. Writing Henry's law as PB equal K prime sub H times XBL allows us to understand why the extrapolation of Henry's law to XBL equal to 1 leads to a y-axis intercept of PB equal to K prime sub H. Sometimes Henry's law is written as a linear relationship between the molarity of the solute in solution, or B between brackets, and the partial vapor pressure of B, and takes the form molarity of B equal K sub H times PB. K sub H is also called a Henry's constant for the solute B in dilute solution with solvent A. We, however, used a different symbol for this constant because it has different units. While K prime sub H had units of pressure, K sub H has units of molarity over pressure. Obviously, given a value of Henry's constant, we will decide how to write Henry's law by examining the units specified for Henry's constant. By analogy with the ideal solution behavior, which is observed when the solvent is almost pure in solution, and Raoult's law is obeyed by the solvent, we define the ideal dilute solution behavior for the solute when the solute is sufficiently dilute in solution and obeys Henry's law. In the same way that we use Raoult's law to express the chemical potential of a species in an ideal solution and the chemical potential of the solvent when it's almost pure, we will use Henry's law to express the chemical potential of the solute in the ideal dilute solution. At equilibrium between a solution and its vapor, we write that the chemical potential of the solute in solution, mu Bl, must be equal to the chemical potential of the solute B in the mixed vapor phase, mu Bg. Then we express the chemical potential of B in the vapor at partial vapor pressure P sub B as the standard chemical potential of B at the standard pressure plus RT times the natural log of P sub B divided by P standard. Making use of Henry's law, we relate the partial vapor pressure P sub B to the mole fraction of B in solution and to Henry's constant, here K prime sub H, and obtain mu Bl, chemical potential of the solute B in solution, equal to mu Bg standard, plus RT times the natural log of K prime sub H times XBL divided by P standard. where we have replaced PB by K prime sub H times XBL. We then isolate XBL from the ratio K prime sub H divided by the standard pressure and obtain mu BL equal to mu BG standard plus RT times the natural log of K prime sub H over P standard plus RT times the natural log of XBL. We then combine the first two terms on the right-hand side of the above equation to form a new hypothetical pure ideal dilute standard state, which we call mu B star, and obtain mu BL equal to mu BL star plus RT times the natural logarithm of XBL. Note that this expression for the chemical potential of a solute following Henry's law appears to be very similar to that of a solvent following Raoult's law. The only difference being in the choice of the standard reference state. For the solvent, the reference state is the pure solvent, a state that indeed exists. The reference state for the solute B is the pure ideal dilute standard state, a state that does not really exist. The fact that the reference state does not exist is not important at all. We have indeed said many times before that we are not interested in values of mu, we are only interested in values for the change in mu with changing conditions. Under such circumstances, the term mu B standard will drop out of the calculation.